Okay. Hello, everybody. This is Professor Ma, and this is the sections on the remainder theorems for Maclaurin or Taylor series. Okay. And first of all, again, we have this page of expansion of Maclaurin series, the formula for expansions, and the most basic ones are the expansion of the most basic function, elementary function, if you like. Okay, just a revisit for revisiting these. Uh, Now, in particular on this list, there's an equal sign. Okay, I mean saying we're actually declaring the series. If you plug in number x, they actually comes out all the same. And then the question comes up is it true if I take a function that's infinitely differentiable and construct its series, is it true? Can I assert this equal sign? That is, the functions and its Taylor series are exactly the same on Maclaurin series. Well, the answer is theoretically no. Okay. For elementary function, turns out to be true. Turn out to be true. If I only stay within these formulas and do all the operations, multiply, divide, subtract, and compositions, then yeah, and then this equal sign is valid. But theoretically, in general, this is not true. Uh, and here's an example. Okay, not true because this function is not elementary. Okay, it's not defined. If I move this part, it just have this function. It is not defined as zero. So there's a hole there. I have to deliberately plug in a hole, and to make it. It turns out this is infinitely differentiable. Not only that, the derivative. It looks like this. It's infinitely differentiable at zero, and the derivative turns out to be zeros. All derivatives. Okay, and I'll leave up. I'll leave you. Leave it up to you to check. It's in the book. It's easy to find out the answer for this case. Well, I'm not going to do the derivation here. Okay. So, in other words, the Maclaurin series of this function is zero. It looks like the line is flat. But the Maclaurin series, of course, doesn't equal to this function f of x. They're different. They're two different functions. F of x is not zero. It's only 0, 0. But p of x is zero everywhere. So therefore, it is not true that a function that looks very nice and infinitely differentiable, very smooth, if you like, that its power series will behave nicely. Okay, if power series might be nothing to do with it, except that agree at one point. Now, so if that's not true, then what can we say about the power series? I mean, over here, the game is still trying to use the power series, the polynomial part of it, the front part, to the nth degree to approximate the values of the function, of the transcendental function. Remember, transcendental means I cannot compute it in finite steps. I'm done. I cannot do that. It's infinite computations. Okay, what can we say about the infinite computations? Well, and this is where mathematicians are coming in general method is something method involved this infinite computation approximations. Usually we describe the method how to do it. On top of that is if we stop doing it at some point, what's the error? Give an estimation of the error. Of course, we cannot find out precisely what the error is. If we can find out precisely the error, then we're done. Okay. The theorems about remainder theorem is uh, what 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 can we say about it? Okay, so here we go. Suppose we have infinite differentiable functions on an interval. Okay, and over here the interval I'm talking about is this interval here, and everything has to be taking place within a close close interval inside that bigger part. Okay, so we can talk about the 0 and b from the point 0 to the point b. Okay, and now I want to talk about what's the difference. Now I'm going to plug in b. So in other words, we are investigating the Maclaurin series. Okay, we're going to set x equal to b. I'm going to plug it into the polynomials, and I'm going to compare that to plugging these functions. Okay, and then the theorem says there is a number c such that when you plug in the b, the difference between them, what we call this the error term, and the error terms can be written in this form, where the c is located between 0 and b. Okay, and we don't know where it is, but there exists such a c. Okay, and in other words, if I plug in the number b into the Mach polynomial up to the nth degree, and that of course is approximation of that, and then the path, that's the difference between the two sides is that part, the red part, except the red part is existent theorems. That is, it tells us there's some c, okay, that will do the job, which is precisely the error terms. Well, I don't know what a c is, okay? And these error terms in this form, when we approximate compare the polynomial versus the function values, this error term, we call this the Lagrange form of the remainders. Okay, there are other forms, there are other expressions that can be utilized in some other ways, but this is called a Lagrange form. Okay, and so what's the use of these theorems? It basically says, okay, the polynomial and the functions equal to, I'm missing by this much, which I don't know really what it is, but it's a formula kind of calculated. Well, the point is, if I can control this part, this involves taking the nth plus first derivative of the function. Okay. And if I can control these parts in general, say that's less than 100, if I know that, that gives me a way of controlling these error terms in its entirety. Okay, in that manner, I can approximate things with certainty, knowing that how many terms have to calculate to gain to be certain of that approximation. We will do that on next section. But let's just first take a look at this formula, what it meant first. Okay. Remark about this formula. It doesn't have to be on the positive side from 0 to b, could be from the negative side, not 0. Okay, so the same thing will apply. Okay, and the value c, of course, changes when you change the number b. If you try to plug in another number, b1, b2 here, and of course the respective c for the approximation will change. Okay. So if I change the number over here b, and if I move it, then the number c is somewhere else. Okay, that's what. And it might be more than one c, but those we'll get to that later. And you can determine c. Okay. So the point is not to find the c. The point is we're going to try to control the entire numerator. So c is included. So let's see what does the remainder theorem tells us about e to the x. Okay. So Maclaurin polynomial of e to the x is these polynomials over here. Okay. So if I write out what the theorem says about the error terms, the Lagrange form, I take the m plus first derivative, which is still e to the x. Okay. And it says, e to the b. Okay. I mean, remember the expansion is around 0, right? 0 to b. Okay. They say e to the b is equal to this much, m plus a little bits error of this much. And some say, what's c? C is somewhere in between a and b. Okay. And if you look at that for a while, then you say, wait a minute, the derivative m plus first of that is still e to the x. So evaluate as c. So this numerator is e to the c. Okay. So in other words, the error term is something looking like that. For some c, it's e to raise to some power c. Okay. For some c, that's between 0 and b. And what's the consequence of that? E to the c is a constant. Okay. This number c is between 0 and b, so this number is certainly smaller than e to the number b itself. Okay, so in other words, the numerator of this fraction is no more than fixed number. Okay, it's a bundle above e to the b. Okay. As m approaches infinity, if I take more and more terms, so if I let n, the polynomial gets longer, n plus 4, degree gets higher and higher, this goes to 0. Okay. And as this goes to 0, so it tells me that the infinite series, therefore fb is equal to sum of 0 to infinity. Okay, b to the k, and k factorial. Indeed, it is, because as the term goes out, m goes to infinity, this arrow terms itself goes to 0. Okay. So this justifies the formula we had in the very beginning, saying that this formula that e to the x actually is equal to the infinite sum, dot, dot, dot. Okay. So that's the first use that we can do, demonstrate that for these elementary formulas, that this convergence, the series actually converge equal to the function value e to the b at a point. Okay. So here's what we go. The largest values, again, we're talking about is error part is e to the b. So we're going to write as k, and then as n goes to infinity, that goes to 0, meaning that the error becomes smaller and smaller if you want the green part as it takes longer and longer. So therefore, the two sides are the same. The series is equal to plugging in. Okay. So we'll come back to the question, when does the max series, okay, if you expand the Maclaurin series of f of x, when is that they are the same? Well, they are the same when exactly that this error term, as you go on, takes more and more polynomial term, the error term has to go to 0. Okay, meaning that the difference between the two sides this side and that side become 0. Okay, therefore, in the series, in the infinite sum, they are equal. Okay, so this is the criteria when the Mach expansion series is exactly equal to f of x. That is, if this error term goes to 0. Okay. So, okay. Now, in terms of elementary function, this is always true. Like I said before, the ones that this where the Mach series and the function are not the same is this one right here. This one which we made it up in the beginning by filling the whole removable thing, removable the point, plugging it in, and this turns out infinite differentiable, but not elementary. Okay. And there's a term for the formula where the Mach series is equal to itself, like f of x equal. The term is analytic. And this function is not analytic, okay, because the Mach series, remember the Mach series of this was 0, Mach series, okay, because the derivative of this is all zeros, of this is p of x is equal to 0. Okay. So here's another justification where the for cosine x that the Maclaurin series is actually equal to cosine x for every x you plug in. Okay, you plugging x into cosine x, you plugging x into the series over here. It doesn't matter what x is. Okay, they're the same. And here's the proof. Basically, you want to prove the remainder term goes to 0, but the derivative, again, but the derivative of this remainder, the derivative of cosine is, change between cosine and sine, and the value of that yellow part numerator is number more than 1. Okay, it's between 1 and -1. And as n become bigger and bigger, the blue part goes to 0. So therefore, the remainder itself r goes to 0. So therefore, cosine x is equal to the series itself. And here's the statements now in Taylor series. Well, Taylor series, that is the difference between Taylor series and the Maclaurin series. The Taylor series, you expand at a point A. Okay, so that's why instead of Maclaurin series, I start with zeros. That's why instead of 0 to B, okay, and for Mach series, now we start from A to B, okay? And everything else statements the same. And this is the Taylor polynomial expansion at around x equal to A, and we want to plug in number B into f of x. Compare f of B with the Taylor polynomial B. And then the Taylor remainder theorem says exactly the same, said that there's a number C in between that fits this formula. And that will be the remainder formula. So in other words, if you're plugging the form B into the formula versus plugging in B for the x, x, and these will be equal to that, but it's off by the error, this much error. Okay, and how much? Well, here's a formula for the error. The next derivative divided by n factorial, n plus 1 factorial. It's called a Lagrange form. Forget of a Taylor remainder. So exactly the same as the Mach series. Okay. Same observations. Okay. And so here's a justification that if you're going to do the Taylor expansion at x equal to pi over 2, and then you are going to get a series basing pi over 2, you can And so here's the expansion. So the justification for you to see this is the Taylor series at pi over 2 sine. Okay. And then the here's a justification that this actually, again, if I were to talk about the error terms, okay. The error terms for Taylor polynomials, Pn and the sign of value at b, it's the same as f of the n plus first derivative is between sine and cosine. So again, it's bounded between 1. So this whole thing goes to 0 as n goes to infinity. And so this sum over here, the tail parts, the arrow terms over here, this part goes to 0. Therefore, the sum is equal to each other. Okay, for every x. Same argument. Which is just writing terms of a different base x minus n. Now finally, we finish with this. If you have a function, its values is equal to a series. Okay, so if you have some power series and the f of x is equal to the power series, and you plug in every number, converges some interval. Okay, then it turns out that series must be the Taylor series, which means a priori this function must be infinitely differentiable. Okay, that's it. So this is the Taylor remainder formula, the implications. Okay, bye bye. And